Okay, so once again, let me just quickly go over the problem. So suppose that you have a shoe company, you're manufacturing shoes, and you have the demand of the next 4 months. Okay? So you have the demand information. So once again, we assume that this information is known to us, so with certainty, so there's no randomness involved. And then we have certain sort of requirements about production. So each pair of shoes requires 4 hours of labor and $5 worth of raw materials. Currently, we have 50 pairs of shoes in stock. And for shoes that we cannot sell, which sort of remain in inventory, we actually pay a cost. And the cost is charged at $30 per pair. And the cost is charged at the end of each month. So if at the end of, let's say, first month, we have, let's say, 10 shoes in our inventory, 10 pairs of shoes, then we pay $300 in terms of inventory cost. Right now, we have 3 workers available, and the salary we pay is $1,500 a month. Each worker can work up to 160 hours per month. Okay? We can hire or fire workers. So basically, this means that we can increase number of workers or we can decrease number of workers. So firing basically means you get rid of that worker. However, those are costly operations. So you can hire a worker at a cost of $1,600. So think of this cost as like training costs, for instance. Okay? And you can sort of fire a worker at a cost of $2,000 and think of this as the sort of benefits that you have to pay. Yes?
Questions.
Sure.
Do they have to work 160 hours or it depends on?
They can work at most 160 hours. Okay? So.
And then
So
hiring worker doesn't make sense because each worker, salary of each worker is 1,500.
Well, that's true, but exactly. So, for example, if the worker actually stays for 2 months extra, then you're better off actually firing that worker, right? So you're actually better off getting rid of that worker. So firing a worker costs $2,000 because there are certain benefits you have to pay and so on and so forth. Okay, so there are certain regulations that you have to take care of. So if you look at the data, the demand data, you see that the data fluctuates, right? So demand fluctuates among different months. So think of these as high season months and these are low season months. Maybe these are boots or something like that. These are winter months and these are summer months or whatever. Okay, so as a result, essentially what you want to do is you want to come up with a production plan, and to be able to implement that production plan, you need a certain number of workers, right? So currently you have 3 workers available. And for example, if the demand increases, maybe you may want to increase number of workers. And if demand decreases, then you may want to decrease number of workers. So you want to adjust the number of workers sort of in your facility. And you have to do it in such a way that your total cost will be as small as possible. Okay? So essentially, this is a problem that we have. And the question is the following. So what are the factors we can control in this problem? So in other words, what are our decision variables? Number of workers, can you be more precise? So number of workers in month I, so that's good. So basically, I'm going to define it by WT. So this is going to be, so these are my decision variables. So this is going to be number of workers.
There are
Permanent.
workers work from first month to the end of
There are no permanent workers though. Okay? So 3 workers is what I have right now. So right now I have 3 workers. I can get rid of them if I want. Okay? So these are not permanent workers. Okay? Nobody's permanent. Okay? So W3 is number of workers working during month T. And T can be equal to 1, 2, 3, or 4. Okay, so that's good. That's something we can control. Anything else? What else can we control? Number of workers hired or fired. That's something we can control. That's good. So let me define by FT. I'm sorry?
You can find these numbers looking at VT?
Well, yes and no. So I'm going to come back to that in a minute. Okay, so FT is number of workers fired at the beginning of month T. And T again can be 1, 2, 3, or 4. Okay, so similarly we can decide how many workers we're going to fire. I'm going to denote it by HT. So this is the number of workers hired at the beginning of month T. What else can we control? How long do they work? Well, it's a constraint actually, right? So they cannot work more than 160 hours. Okay? So that's not really a decision variable. That depends on something else though. What does it depend on? How many shoes we're gonna produce actually, right? So because for shoe production we need labor. Okay? So there are two other decisions we need to make. So for example, since we can actually carry inventory, what I can do is I can produce everything in the first month and I can put everything in inventory, for instance. That would be an option. Or I can only produce as much as I need and I can carry no inventory. So these are decisions I can make. Okay? So I'm going to denote by P sub T. So this is going to denote the production amount. So this is number of pairs of shoes. Number of pairs of shoes produced or manufactured during month T. And T can be 1, 2, 3, or 4. And what else? Well, depending on that, we have certain inventory basically, right? So I'm going to define it as a new variable as well. I'm going to call it IT. IT is the number of pairs of shoes in inventory at the end of month T. So remember, I'm defining the number of shoes at the end of the month in inventory. So as a result, since I have initial inventory, I'm going to start it from 0 this time. Okay, because I0 is the amount of inventory I have right now. So T will go from 0 to 4. So the reason why I'm including 0 is because I0 actually corresponds to my current stack. Okay? And that's going to make our formulation easier, basically. So these are my decision variables. Now, let me try to formulate the problem. So I'm going to try to minimize the total cost. Okay, so I need to figure out what the total cost is. So since this is a cost minimization problem, I'm going to start with min. So let's try to identify our sort of source of cost, basically. Okay, so what kind of cost do we have for this problem? Well, so if I go back to this example, so let's try to do it in order. So first of all, we have the cost of raw materials, right? And what does this depend on? Number of shoes we're going to produce, basically, right? So basically, in each of the 4 months, I'm going to actually pay $5 for each pair of shoes I'm going to produce. Okay? So how can I include in my objective function? So I'm going to have 5 times PT, but I have to look at each of the 4 months, so T will go from 1 to 4, basically, right? So this is the cost of raw materials, basically. Okay? All right, so I'm looking at the cost factors again. There's an inventory cost, okay? And it's charged at $30 per pair. So how am I going to include in my objective function? Just look at the decision variables. So IT is the number of pairs of shoes in inventory at the end of month T. Okay? So I'm going to multiply 30 by IT, basically, right? So well, note that T actually starts from 1 to 4, okay? So you may be wondering about, well, over there we started T from 0, right? And the reason for this is the following. So because we assume that for the current stack, okay, we already paid this cost. Okay, so I'm only looking at what's going to happen from now on. Okay, I already have some inventory and I already paid the cost of inventory before, so now I'm looking ahead. Okay, so what am I going to do from now on? What else? So the next one is this one, I guess. So we have the cost of the salary of each worker. So for each worker I have, I'm going to pay 1,500. Okay, and I'm going to multiply that by the number of workers I have, basically, right? So what's the number of workers I have? WT. And then we're done with the costs over here. So we also have hiring costs. Okay. So the cost of hiring a worker is 1,600, and HT is the number of workers hired at the beginning of month T. So I'm going to have 1,600 times HT. Okay. And finally, what else do I have? Firing costs. So I'm going to have 2,000 times FT. And then I'm going to put this in parentheses. Okay, so for each period, I'm going to actually add up these costs, and I have 4 periods or 4 months, and this is going to give me the total cost. Okay, so once again, this is the cost of raw materials, cost of inventory, cost of salaries, cost of hiring, and cost of firing. Okay. Now, what are my constraints? So let me start with the current inventory. Okay, what's my current inventory level? It's equal to 50 actually. How can I write as a constraint? Well, I0 corresponds to number of pairs of shoes in inventory at the end of month 0, which is at the beginning of month 1 basically. Okay, so I0 should be simply equal to 50. Okay, so this is the current inventory level. Okay. All right, so then what else do we have? Well, try to think of it this way. So right now, let's say we're in month T. Okay? And in month T, we're going to have a beginning inventory. Okay? So beginning inventory, let's say. And we're going to also have production during this month. And the sum of these two will give us total number of shoes we can sell, basically, right? Okay, previous inventory plus whatever you produce is the total amount of total number of pairs of shoes you have on hand. And from this one, you're going to meet the demand. And then the remaining ones, if any, becomes the ending inventory. Right? So you have basically two sort of inputs and two outputs, right? So beginning inventory plus production should be actually equal to demand plus the ending inventory. Okay, so to simplify my formulation, I'm going to define the following. I'm going to define dt, and this is going to be the demand during month T. And T will go from 1 to 4. But one thing that you should pay attention to is that this is not a variable actually. Okay, so dt actually is a parameter. In other words, dt is something I cannot control, it's already given to me. Okay, so d1 is equal to 300, d2 is equal to 500, and so on and so forth. So I have no control over this, but this is going to just make my formulation a lot easier, basically, a lot simpler. So now, how can I express, the relation in the chart as a constraint? Well, for month T, I'm going to have some beginning inventory. Okay, so what's the beginning inventory for month T? So just look at how I defined my inventory variable. So I define it at the end of month T, right? So basically, at month T, I'm going to look at the beginning inventory. But the beginning inventory of month T is the same as ending inventory of month T minus 1, basically, right? So as a result, I'm going to have IT minus 1, which is the beginning inventory, okay, plus the production amount, which is PT. So this is going to be total number of shoes I have available during month T. And from this, I'm going to actually satisfy my demand, which is DT. And then after satisfying demand, I may still have some shoes. That's going to be my ending inventory, right? So what's the ending inventory? IT, exactly. And I have this relationship for each of the 4 months. And note that if you put everything on the left-hand side, this just becomes an LP constraint, basically, right? Okay? So this type of relations are extremely important, basically, in this type of problems, because these are called balance constraints, okay? You have the inputs should be the same as outputs, okay? The input is the beginning inventory plus production, and the output is demand plus the ending inventory, okay? And the output from this month, which is IT, actually becomes the beginning inventory of next month, okay? So there's a sequence of relationships, basically, and more precisely, there's actually 4 of them. And we have these balance constraints, so these are known as inventory constraints, basically. Inventory plus production should be the same as demand plus the ending inventory, okay? So all of the decision variables should satisfy this relationship. Is that clear? All right. What else do I have? Well, I have a similar relationship for number of workers, basically, right? So again, at the beginning of each month, I have the current number of workers. Plus, I can actually hire some workers. Then I can fire some workers. And then I'm going to have some leftovers. Okay? So in terms of production, I'm going to look at it in terms of number of workers, basically. So what's the number of workers at the beginning of month T? So, well, since hiring decisions are made at the end of each month, basically, number of workers working during month T is the same as number of workers that will start to work in month T as well. Okay? So, in other words, WT minus 1 is number of workers coming from the previous month. Okay? Now, to this, I can actually add some workers. Okay? And that's going to be equal to HT. So, this is the number of workers I'm going to hire. So, number of workers coming from the previous month plus number of workers I'm going to hire. Okay, is going to be the same as I may fire some workers, right? And then the remaining ones actually will work for me. Okay, so one thing that's important to realize here is the following. So this is number of workers coming from the previous month. Okay, then I'm hiring some workers and I'm firing some workers, and the remaining ones will be the number of workers I have in this month. Okay, and I need this to be true for each of the 4 months as well. Is that clear? So this is pretty much like the production balance constraints. I'm writing this in terms of workers. So basically input is the same as output. Okay? What is the initial number of workers I have right now in my system? So it's equal to 3. So just like the initial inventory, the initial number of workers is equal to 3. Anything else? Well, we meet the demand here, basically. Okay, so this makes sure that we meet the demand. Exactly. So we cannot actually have a worker work more than 160 hours. So how can I write as a constraint? So remember, each pair of shoes requires 4 hours of labor, right? Okay. And if I multiply this by the number of pairs of shoes I'm going to produce, then that's going to give me a total number of labor hours, basically, I'm going to use. And that cannot be more than 160 times the number of workers that I have. Okay? So how can I write as a constraint? Four times PT is the total number of labor hours I'm going to need to carry out this production. Cannot be more than 160 times WT, right? And I want this to be true for each of the 4 months. So this makes sure that I cannot exceed the available labor hours, basically, okay? So this is total labor hours available. This is total production requirement. And this says to be true. Anything else? We have non-negative, exactly. So I'm going to start with WT, FT, HT, PT, and IT should be non-negative. And this is true for all T. So this is just a shorthand notation. So this basically means that each of them should be non-negative. Okay. Anything else? Exactly. So if you look at the variables, actually none of them is divisible, basically, right? So WT, FT, and HT refers to number of workers. PT and IT refer to number of pairs of shoes, and none of them is divisible. So as a result, they should all be integer valued. So FT, WT, HT, PT, and IT should be all integer valued. And if I solve this problem, then I can figure out my production schedule, okay? So once again, just to make an important remark, so dt is not a variable, okay? The reason why I define dt is because then I can write my constraints in this way, okay? So as a result, dt is something I cannot control, so it's a parameter of the problem. I have 5 decision variables. Well, I have 5 sets of decision variables, because for each one there's actually 4, 4, 4, 4, and 5. So I think I have a total of 21 decision variables, okay? And I have my constraints. And note that basically I have 4 constraints here, right? So 1 for each month. I have another 4 constraints here. I have 1 equality constraint here, 1 equality constraint here, and then I have another 4 constraints. Then I have the non-negativity constraints, and so on and so forth. Okay? So once again, I mean, the sort of main message of this example is these 2 equations, basically. Okay? So these are called balance equations. So whatever comes in should be the same as whatever comes out. Okay? And this type of equations actually arises in a lot of different settings. So for example, we're going to see some examples later on, some other examples later on. So try to think of the following example. For example, suppose that you're shipping some goods to certain points, and you have a certain distribution center. Okay, so the goods actually may arrive from different sources, and then they should be routed to different retailers. Okay, so here we have a similar situation. So the incoming products should be the same as outgoing products, basically. Okay, so whatever comes in should be the same as whatever comes out. And if you think about this, this is precisely the same picture. Okay, so if you think of this as my sort of point, basically, okay, my circle. So these are the inputs, and they should be the same as the outputs, okay? And in both cases, both for the workers and number of pairs of shoes, we have the same type of relationships. Okay? Any questions? So once again, I mean, they're really important, so if there's anything not clear, this is a good time to ask. Okay? All right, so this is an example of a workforce scheduling problem. So now we're going to sort of define a new concept, and that's going to help us a lot. This is example number 14. So this is known as the 0-1 knapsack problem. So suppose that you are going on a trip, and your suitcase has a capacity of B kilograms. So think of B as some number, like 10 or 20 or 25, depending on how big your luggage is. Okay. So let's assume that you have n different items. Labeled 1 through n. So your sweater, your pair of pants, you have your socks and whatever. So you have n different items you can pack. That you can pack into your suitcase. So we're going to assume that item I has a weight of AI. And gives you a value of CI. Again, I goes from 1 to n. And the question is the following. So how should you pack your suitcase your suitcase to maximize your total value. It's a very simple problem, actually, to describe at least. So you're going on a trip. You have a suitcase, which has a capacity of b kilograms, so you can pick at most b kilograms into your suitcase. You have n different items, which we label 1 through n, so item 1, item 2, and so on and so forth. And item 1 has a weight of A1, item 2 has a weight of A2, and so on and so forth. Again, these are given in terms of kilograms. And item I gives you a value of Ci. So for example, item 1 is important for you maybe, and so C1 is large. Item 2 is not so important, so C2 is not so large, and so on and so forth. And what you want to do is you want to sort of figure out how you should pack your suitcase so that you maximize your total value. Okay? So where does this problem come from? Well, for example, if you fly somewhere, right, so they have a sort of luggage capacity, right? So you cannot pack more than 20 kilograms, and if you do, you pay extra. So you may assume that you don't want to exceed that, so you don't want to pay extra, so you should decide how you should pack your knapsack. Knapsack basically means backpack, okay? What else? So another application of this problem is, suppose that you're a thief and you're robbing a place, and what you want to do is you want to sort of maximize total value of your items, but you can carry only so much, so as a result, what items should you steal? Of course, you're not going to steal, but just in case. So this is an example, okay? And it has many other interesting applications, okay? So it's a very sort of simply defined problem, okay? It is a very simple description. So essentially, for each item, you're going to make the following decision: should I pack this item or not? Right? So should I actually include this in my suitcase or not? And you have n items. So as a result, you have a finite number of items, and for each item, you're going to sort of decide whether you should pack that item or not. Okay? And you have a value of each item. And the question is, how should you maximize your total value, or how should you pack your knapsack to maximize your total value? Is the problem clear? So, all right. So, what are my decision variables? Well, this is kind of a strange problem, right? So, this looks different from the problems that we've seen earlier. So, so here I'm facing a sort of different type of decision. Should I take item I or not? Okay. So, whereas in the previous problems, we always try to define our decision variables in the following way. So, xi is the number of, for example, products or number of workers or something like that. So, the question is, how can I define my decision variables for this problem? Well, so just like we did in the previous problems, I can define xi to be the number of units of item I I'm going to pack in my suitcase, right? Okay. But there's one difference. So number of items that I can pack into my suitcase can only take two values, basically. It can either be 0 or 1. Okay? Because for each item, I have only one of them. Okay? So as a result, essentially, I'm going to use that fact, and I'm going to define my decision variable in the following way. I'm going to call it xi. And I'm going to say that xi is equal to 1 if item I is packed in my suitcase. And I'm going to define it 0 otherwise. And I'm going to define it for each of my decision variables. So I have n of them. So as a result, each of my items, sorry. So as a result, I have n items and n decision variables. And if you think about this a little bit, xi is essentially the same as number of units of item I I'm going to pack, basically, right? So with the only exception that xi can only be 0 or 1. Okay, so I can either take 0 units of item I, or I can take 1 unit of item I. That's why it's called the 0-1 knapsack problem. Okay? All right. Now, how can I express my objective function? So I want to maximize my total value. How can I express my total value in terms of my decision variables? So I'm going to maximize the following. So if I pack item I into my suitcase, I'm going to get a value of Ci, right? And if I don't pack that item, then I'll get a 0 value, basically. Now, if you think about this a little bit, so if I multiply Ci by Xi, okay, then if Xi is equal to 1, I'm going to get the value of Ci. And if Xi is 0, then I'm going to get nothing, okay? And if I simply sum this up over all of my items, then this is exactly total value that I'm going to get, okay? Because each of the components will be either equal to 0 or 1, which means that each of these terms will be either equal to Ci or 0. Okay? So it's equal to Ci if the item is packed, and it's going to be equal to 0 if the item is not packed. Does everybody agree that this is correct? All right, so what are my constraints? So I have a capacity constraint. Right? So I need to make sure that the total weight of my items cannot exceed the capacity of my suitcase. So how can I express it as a constraint? Well, by the same reasoning. So if I multiply Ai by Xi, that's going to give me the contribution of item I towards the total weight. Right? So if Xi is equal to 1, then item I will contribute Ai towards total weight. And if Xi is 0, then that item will contribute nothing. Okay? And if I sum this over all items, this is going to give me a total space requirement, right? Okay? And so this is going to be the total weight of the items I'm going to pack. And obviously this cannot be more than the capacity of my knapsack. Okay? So total weight of the items I'm going to pack cannot be more than the capacity of my suitcase. Okay? So this basically is the capacity restriction. What else? Well, remember, so my decision variable Xi can only be equal to 0 or 1. Okay? Which I can express it in the following way. So I can say that Xi is greater than or equal to 0. Right? I can say that Xi is less than or equal to 1. And then I can say that Xi is integer. And if I actually add these constraints, they make sure that Xi can only be equal to 0 or 1, basically, right? So this says that Xi should be non-negative. This says that Xi cannot be more than 1. And this says that Xi should be integer. Well, I don't have too many choices, right? So Xi can be either 0 or 1. Yes?
You already mentioned about Xi. We need to rewrite it.
Yes, we do, because there we define our decision variables. Here, I'm constructing my model. Okay? So think of, I mean, these are two different entities, so to speak. Okay? So these are two different sort of parts. So here I define my decision variables. Here I'm writing the model based on my decision variables. Okay? So my model doesn't know what my decision variables are. Okay? So I need to tell my model what they are, basically. Okay? So as a result, if I do this for all I, then obviously it's not too hard to see that these are just valid LP constraints. Okay? When I add this, it becomes an IP problem. So as a result, this is an example of an IP problem, right? Okay? So from now on, whenever we see variables of this type, instead of writing it this way, we can actually write it in the following way. So instead, we're going to say Xi can be either 0 or 1. Okay? And I can go from 1 to n. So basically, we're going to replace these whole constraints by this one. Okay? With the, of course, understanding that these constraints can be written as LP and IP constraints. Okay? So instead of writing it this way, we're going to have a shorthand notation. So we're going to simply say that Xi can be either 0 or 1. Okay? And once again, it's important to realize that this sort of special constraints is just equivalent to these constraints right here. Okay? So as a result, writing it this way does not change my problem. Okay? My problem is still an IP problem, basically. Okay? Now, let me talk a bit about these variables. So in this problem, Xi can be either 1 or 0. Okay, so this type of variables actually has a special name. Okay, so what do we call it? Any suggestions? Sorry? It's not Bernoulli, but it's binary actually, right? So we call it actually binary variables. And binary variables are great, actually, okay? Why is that? Because they can model all sorts of yes-no type decisions, okay? Like, should I do something or not? If I do it, I'll set it equal to 1. If I don't do it, I'll set it equal to 0. In this problem, should I pick item I or not? If I pick item I, it's going to be equal to 1. Otherwise, it's going to be 0. So as a result, whenever you have this yes-no type decisions, should I do it or not, you will always have to use binary variables, okay? So as a result, binary variables actually give you great flexibility in terms of modeling, different types of decisions, such as this one. For example, you're, let's say, coming up, you're trying to decide which courses you should take. For example, if I take, Math 101, that variable will be equal to 1, otherwise it's going to be 0. If I, for example, if I go to cafeteria and if I order this particular item, it's going to be equal to 1, otherwise it's going to be 0. Okay? So there are a lot of things in life that you can actually formulate using binary variables, and this is just one of them. Okay? So as a result, whenever you have a yes-no type decision, binary variables actually help you a lot. Okay? So with binary variables, you can always sort of formulate the sort of type of yes-no decisions. If it's equal to 1, then it's a yes decision. If it's 0, then it's a no decision. And this would be an example, basically. Okay, so here I'm trying to decide whether I should take item I, in which case the corresponding variable is 1, and if I don't take it, then it's going to be 0. Okay? Any questions? All right, just a quick application of this. Binary variables. So this is example 15. And this is known as a set cover problem. So the question is the following. So you wish to decide where to install hospitals in the city, where to build hospitals in the city. So suppose that there are 5 potential, suppose that there are 5 towns to be served, and 4 potential locations. 4 potential locations to build hospitals. And we're given the following matrix. So these are towns, and over here are potential locations. So I have 4 of them, and I have 5 towns. And in this matrix, I have the travel time in terms of number of minutes. So I have the following information: 10, 15, 20, 10, and 16. And then 15, 10, 8, 14, and 12. Then 8, 6, 12, 15, and 10. And then 12, 17, 7, 9, and 10. So basically think of this as a travel time matrix. So to go from potential location 1 to the first town, I need 10 minutes basically, or it takes me 10 minutes. Going from potential location 1 to town 2 takes me 15 minutes, and so on and so forth. So we have the following requirements. Travel time between each town and the nearest hospital. And the nearest hospital should be less than or equal to 10 minutes. So basically, when we're sort of building hospitals, we need to make sure that for each town, the distance between travel time between the town and the nearest hospital should not be more than 10 minutes, so that in case of emergency, I can get there in at most 10 minutes, right? So whatever happens, I can actually be there at most 10 minutes. And the question is the following. So what is the minimum number of hospitals that I should open? that should be opened. And of course, where should I open them? Okay, so not only I'm interested in the number, but I'm also interested in which locations should actually have hospitals. So think of it this way. There are 4 potential locations where I can build hospitals. And there are 5 towns that I need to serve. Okay, think of it as a city, for example. And these are the travel times between each potential location and each town. And what I want to do is I want to actually pick among these 4 locations. I'm going to pick some number of them. Okay, and at those locations I'm going to open some hospitals. And I want to do this in such a way that the travel time between any town and the nearest hospital should not be more than 10 minutes. Okay, so for example, if I have a hospital in the second location, and then this hospital cannot serve the first town, basically, right? Because travel time is more than 10 minutes. Okay? So the question is basically, how can I do this by opening the smallest number of hospitals? So another way to think about this problem is the following. For each town, there should be a hospital within 10 minutes. Okay? All right, so now what are my decision variables for this problem? Well, once again, this is kind of similar to the previous problem, right? So what kind of decisions am I facing? Well, for each of the 4 locations, 4 potential locations, should I actually build a hospital or not, right? So the city actually shows me 4 potential locations and asks me whether I should open a hospital at this location or not. Okay, so what kind of variable should I use? Well, just like the previous example, I'm going to use binary variables. I'm going to define xi in the following way. So it's going to be 1 if... So how should I complete the definition? If we build a hospital at location I. And it's going to be 0 otherwise. And since there are 4 locations, I'm going to have 4 decision variables. So I goes from 1 to 4. Okay? So once again, I mean, this is a perfect example. So at each location, I have a yes-no decision. Should I actually open a hospital here or not? Okay, so depending on my decision, xi will be equal to either 1 or 0. All right, so now what is my objective function? I want to minimize the number of hospitals. So how can I express the number of hospitals in terms of my decision variables? Sum of xi's, exactly. So if I simply add xi's, x1 through x4, this is precisely the number of hospitals that I'm going to open, right? Why is that? Because each xi either contributes 1 or 0. And if I look at their sum, the sum is precisely the total number of hospitals I'm going to open. Does everyone see that? All right. Now, what are my constraints? Well, what are the requirements? So for each town, the distance between that town and the nearest hospital should not be more than 10 minutes. So what does that mean? So for example, if I look at town 1, okay, so these are travel times from each potential location to town 1 in the first column, right? And in the first column, for example, only potential locations 1 and 3 actually can serve the first town, right? In other words, if I open a hospital only in location 2 or location 4, then I cannot serve town 1. Okay? So in order to serve town 1 properly meaning with respect to these requirements, I should either open a hospital here or here, basically. Okay? So the question is, how can I write this as a constraint? Okay.
Y, I, J.
Okay.
Which shows I towns and J
potential location.
Okay.
Then we can set it less than or equal to 10 for each town.
So YIJ will denote what? So,
Yani bir tane değişken kullanırız, YIJ diye.
okay.
Böylece bütün town ve potential location'lar için ondan küçüklük eşit olmasını sağlıyorsa hepsinden eşit olmaz. O yüzden bu
No, that's good. So, I'm always open to suggestions. So, let's just focus on the first town, okay? So, now to serve the first town properly, I should either consider opening a hospital here or here, basically, right? In other words, if I don't open a hospital in location 1, and if I don't open a hospital in location 3, then I cannot serve the first town, okay? So what does that mean? Well, if I look at these numbers here, among these numbers, only these two locations would be okay for me to serve town 1. Okay? So how can I write this as a constraint? Well, if I look at potential locations 1 and 3, at least one of them should have a hospital, basically. Right? Why at least one? Because I can actually both open hospitals in both locations, but at least one of them is enough for me to serve the first town. Okay? So how can I write this as a constraint then? Well, remember x1 denotes the variable corresponding to opening hospital in the first location, and x3 denotes the variable that corresponds to opening hospital in the third location. Okay? So what is the summation? This is number of hospitals I'm going to open in 1 and 3rd locations, in the first and third locations. Okay? So I want to make sure that this is going to be at least 1, basically. Why do I need this? Because by ensuring this, I know that I can serve town 1 properly. Okay? So this basically says that between the first and the third locations, you should pick at least one of them. Does everyone see that? Okay. So what is the constraint for the second town? Well, now I should look at the second column of that matrix. Okay. To serve the second town properly, I should either consider opening hospital in the second location or the third location, basically, right? Okay. So what's the corresponding constraint? x2 plus x3 should be, by the same reasoning, at least 1. Okay, so at least one of them should have a hospital, basically. Okay? Now let me move on to the third town. So in order to serve third town properly, so where should I consider opening hospitals? Second and fourth locations. So x2 plus x4 is at least 1. Why am I saying at least 1 instead of exactly 1? Because of the following reason. So, for example, in the first, for the first town, maybe x1. If x1 is equal to 1, then that already serves town 1. But by setting x3 also 1, maybe serves some other towns as well. Okay. So the fact that I'm opening a hospital in town 1 does not actually prevent me from opening a hospital in town 3. Okay. What else? What's the first for the fourth town? We have x1 plus x4, right? Is at least 1. And for the last one, we have x3 plus x4, right? Should be at least 1. So what else do we need? Well, each xi is a binary variable. So xi can be either 0 or 1 for I from 1 to 4. So by solving this problem then, I can actually decide how many hospitals I need, and I can also decide where to open those hospitals, okay? So in the optimal solution, if x1 is equal to 1 and x4 is equal to 1, then I'm going to actually do it with only 2 hospitals, and I'm going to open a hospital in the first location and in the fourth location. Any questions? All right, I'll see you next time.